On days I decide that I'm going to do things perfectly, I think I do everything wrong. Yeah, fine. Thank you very much. Yeah. So your B was essentially root of m alpha by um, h cross. And how do you write down your psi of x? So this is something I was urging you people to try and remember. Okay, that if you see a psi of x like this, please know that there is a Dirac delta potential at play. So in all your competitive exams or your interviews, okay, very often people may ask you to identify a potential looking at the form of the wave function. So try and connect the dots. All right. Yeah, so this is e to the power of minus, and then you have root of m alpha, right? Yeah, m alpha by h cross square. Yeah, and then you have a mod x. Okay, so this is basically your wave function. Now what we were doing after this was that this we solved for the bound states, and now I said that we will, last time we were trying to do this. Okay, we were trying to do it for the scattering states. Okay, and scattering states of course is essentially for e greater than 0. Of course you have the same situation now. um, what So let me just run through the argument, and then at some point we will start doing it in a bit of detail. So the argument is something like this. You now have h cross square by 2m d square by dx square psi, and then what you do is essentially, one second please, yeah, you would go ahead, yeah, for anywhere for this x not equal to 0, okay, any region which is x not equal to 0, your potential of course goes to 0, and so you have just this e psi x on the other side, right? So this implies that you would have your d square psi by dx square, okay, plus 2 me by h cross square psi equal to 0, and this of course you will put as some k square, and then what do you get as your solution? So please remember your k is going to be nothing but root of 2me by h cross square, and this is something that you're all familiar with, and your solution of course is going to be psi of x is going to be a e to the power of I k x plus b e to the power of minus I k x, right? I think we had done this already, and this, if it is, we can take this for x less than 0. We'll have to have two solutions, one for x less than 0, one for x greater than 0, and here we put it as some f e to the power of I k x plus g e to the power of minus I k x. Okay, this is for x greater than 0. And what we have to do is by using continuity conditions, okay, so using continuity conditions, at which point the only point of contention over here, okay, which is x is equal to 0, conditions at x is equal to 0, all right, okay, we find relation between a, b, f and g. Okay, so this is the basic idea, and if you remember, this is what we were trying to do last time. Okay, so for continuity for psi, continuity for psi, okay, would essentially imply that your this factor and this should be equal for x is equal to 0, which essentially leads you to a plus b is equal to f plus g. I think we had done this already last time. Okay, now the next factor which we need, okay, let me remember to at least change the page since I'm doing such a lot of goofing up today. Okay, yes, I change page. Okay, and then the other factor was of course linked to d psi by dx. So what we had discussed last time, if you remember, that since your potential goes off to infinity at x is equal to 0, your d psi by dx is not continuous. Okay, so this is a factor that you have to remember, that your d psi by dx will be continuous only if your potential has not shot off to 0. Okay, all right. So now let us just see. So, but we had already figured out that your delta d psi dx, okay, at x is equal to 0. Just one second. Where do we? Yeah. So over here we can do it as d psi dx approaching x tending to 0 from the positive side minus d psi dx x tending to 0 from the negative side. Correct? Yeah. And what was the form for psi of x for x greater than 0? X greater than 0. It is nothing but f e to the power of ikx plus g e to the power of minus ikx. So obviously your d psi dx is going to be essentially ik f e to the power of ikx. Then you have minus ik g e to the power of minus ikx. So this at x equal to 0 will essentially give us, we can take out the I and the k, and we will get essentially f minus g, right? This is what we will get. And similarly, okay, we can say that this d psi, so this is dx at x tending to 0 negative will give us essentially ik into again a minus b, right? And what we will get now is essentially your from what we already derived for the bound state itself, your d psi delta x, okay, is also equal to minus 2m alpha by h cross square, okay, psi of 0. Okay, so this is basically what we have, and therefore this implies that ik f minus g minus ik a minus b, okay, must be equal to minus 2m alpha by h cross square. So let's decide that we are going to take the psi 0 value. Okay, so psi 0, we are going to put the value for x going to 0 from the negative side. Okay, so in which case we will get a plus b. Okay, yeah, so you can just look at the wave function and you realize that is true. So now what do you get? Essentially, you will get over here ik into f minus g, okay, is equal to minus m alpha by h cross square a plus b plus ik a minus b. Correct? So this is now going to be equal to, okay, so we can divide by ik throughout, which implies that your f minus g is going to be essentially minus m alpha divided by ik h cross square a plus b plus a minus b, right? So this is what we get. So we can then further write this as, okay, yeah, we can write this as I into 2m alpha. Okay, I don't know why I did this step. Strange. Okay, anyway, doesn't matter. H cross square a plus b plus a minus b, and then you can write this as essentially you put this factor, okay, m alpha just by k h cross square is equal to some beta. Okay, so you will have essentially 1 plus 2I beta times A plus 1 minus, do I get a minus? Maybe I'm making a mistake. I think this should be a minus. Then I can write it 1 minus 2I beta B. Is this correct? Are the signs correct? I hope so. Yeah, I think they are. All right. So this is what we get. All right. Now, what you have to understand over here. So this is where we will, use some kind of intuition of what is really happening. See, we have factors A, B, F, and G. Okay, so let us try and imagine what these are representing. So we already know these are scattering states, right? So let us kind of draw the x-axis. So this is your x-axis, right? This is x, all right? And this is, let us say, x equal to 0. Okay, and here you have your potential going off to, okay, it is basically going off to an infinitely deep potential. Okay, not a very good drawing, I'm sorry. Okay, so this is what it is. All right, so this is essentially your v of x, and it's heading off to minus infinity here. Correct, this is basically the situation. Now what have we said? That our wave function looks like a e to the power of ikx plus b e to the power of minus ikx. So thinking in terms of your wave functions, if you put in the time dependent part as well, you will realize this a is essentially representing a plane wave which is moving towards the right, correct, from below x is equal to 0, and b essentially represents a plane wave which is moving towards the left for x less than 0. Okay, so in some sense this is your incident wave. Okay, we can take this to be an incident wave. You can take it the other way around also, it's not a problem, but let us assume that this is the incident wave, in which case this becomes the reflected wave. Correct, yeah, this is going to become the reflected wave. So it's scattering off the potential and it is going in the opposite direction to the incident wave. Then automatically, if you go to this side, you have an f e to the power of ikx plus g e to the power of minus ikx, right? So thereby this means that you have your f, okay, wave basically means that it is a transmitted wave. Correct, it is going past the potential, it is on the other side of the potential compared to where the incidence is coming from. Okay, you could have taken it the other way. Please note, you could always take that the g is the incident wave, okay, and just move from there. Okay, that is also not a problem. All right, anything that is moving towards the the potential, one of them you can take as an incidence. All right, so here I'm just taking that the incidence is happening from the left side, but there is nothing sacred about it. Okay, the solution would still work either way. All right, you need that information beforehand, whether the incidence is from the left or the right. But otherwise, if you're not given that information, both the cases are equivalent. Now comes the basic thing, is that your g now is something that is coming from large x, okay, towards the potential. But if this potential is in isolation, this has no meaning. Okay, so what you can do now is set this guy to 0. Okay, so this is basically where you are not just doing the mathematics, but you're bringing in the physics of the situation and saying that, hey, if this is a scattering problem and I take my incidence either from the left, in which case g goes to 0, and if the incidence was from the right, what would go to 0, please? Equivalently, oh, I lost. I think I lost connection. Just give me a second. I'm going to try and put it on the dongle, okay? Because it's going on telling me that my internet connection is unstable. Just hang on a second, or 1 second. Let me just see if I'm on the wrong Wi-Fi. Okay, maybe I am. Sorry about that. Yeah. Somehow it is connecting to a point somewhere else. Okay, come on. Yeah, this is a problem. I also have a slow computer. Yeah, so another way I goofed up today. All right. So I hope, yeah, I'll do that, Nitin. Thank you. Sorry about that. Yeah, I think I just disappeared mid explanation. I'm really sorry. Okay, so let me get back to share screen. Yes. Okay. Right. So let me just repeat this whole thing, what I said. So please note, okay, your potential is sitting at x is equal to 0. It is going off to minus infinity over there. We are trying to solve now for E greater than 0, which means we are trying to solve for the scattering states. Okay. And as you kind of saw, the solution will be below x is equal to 0, some a e to the power of ikx plus b e to the power of minus ikx. And for x greater than 0 region, you will have an f e to the power of ikx plus g e to the power of minus ikx. Okay. So essentially what you can recognize is these are plane wave solutions, correct? Now, let us imagine that the incidence, okay, so the scattering is going to happen from one side or the other. Okay, so let us imagine that the incidence is happening from the left. Okay, so something is coming from the left and scattering off this potential. So in which case you will identify your a e to the power of ikx as your incident wave. Okay, so a is coming in. All right. Then, of course, what is moving opposite to the direction in the same region, okay, so x less than 0 in the same region, what is going opposite from that potential is going to be the reflected wave. Now look at the other side. If a is incident, b is reflected, then obviously f e to the power of ikx, which is essentially moving in the same direction as the incidence but on the other side of the potential, must be the transmitted wave. Okay. Then now your g e to the power of minus ikx, okay, the interpretation of that is unclear, right? Simply because you are considering this potential in isolation. You're not saying that, oh, I have this potential and I have something else at larger x. You are solving for the delta function potential alone. So it's an isolation. So there is no reason that you should have a wave coming in from large x or x greater than 0 when you have already assumed that the incidence is from coming in from the left, that is from x less than 0. So there's no reason for something to be coming in from x greater than 0. So thereby you put your g equal to 0. What I was trying to say is that I have just told you that the incidence is from the left. There is nothing sacred about it. You could have the incidence from the right, but this is an information you need prior. And you have to remember that the incidence has to be either from the left or from the right. It cannot be both. Okay. Because you're going to do it particle by particle, right? I mean, one particle scattering, then another particle scattering, and so on and so forth. So thereby, as I said, knowing that, okay, you will, so for instance, as I said, if the incidence was from the right, from x greater than 0, then obviously your g becomes your incidence. Okay, it's the amplitude of the incident wave. Your f becomes reflected. And then which factor goes to 0, please? That's what I was asking before I disappeared. So which of these a b c d a b f g goes to 0 then, if your incidence is from the higher x's?
A is going to be 0.
Yeah, a will go to 0. Okay, but remember the solution form remains the same. Okay, there's not going to be any change. So now, since we have identified a as incidence, B as reflected, okay? I'm just talking about the amplitudes of the waves. Your F is transmitted, and G now becomes physically, you have to put that equal to 0 because there's no physical interpretation for G, okay, being non-zero. Now, what you realize is that it perhaps not only it makes our equation easier, of course, yeah, because you can see there is an F minus G that just becomes F, right? Because G goes to 0. It also makes sense for us. So we are now dealing with three unknowns, right? We have your F, you have your A, and you have your B. It makes sense for us to write B and F in terms of A. Because incidence, you can imagine that there is somebody who's going to control, okay, who's going to decide what is the incidence, what is the amplitude of the incident wave is going to fit. So in some sense he's deciding the intensity of the incoming wave, okay. So A is out of our control, but given an A we should be able to identify what is the B and what is the F, which is why please remember in scattering problems, okay, you always figure out what is reflection coefficient, what is transmission coefficient, okay. I hope this is kind of clear. I mean, you would have done this in your 1D problems, okay. See, because sometimes you wonder, why are you bothering with bound states, why are you bothering with scattering? So scattering states, please remember, since the incidence is out of control of the problem parameters, okay, in such a case what happens is that you always end up calculating your reflection and your transmission coefficients, which essentially are ratios of, as I said, the B to A, which would give you the mod of that whole square would give you your reflection coefficient, and your F to A, which the mod of the whole square would give you the transmission coefficient, okay, or the transmission, okay, you can say it whichever way. So this is the basic thing which I think I'd written up and sent. I had done it in a bit briefly. So here I will just work it out now. What is your reflection and your transmission? So just let me change page. As I said, amongst all the goofy things that I've done, let me not add more to your agony. All right. So now, what will we get now? If you remember, what was our final thing? I shouldn't have thrown it away. What did we write finally? We wrote that F minus G is equal to 1 plus 2I beta A, sorry, minus 1 minus 2I beta B, right? Yeah. And then of course we are going to put G equal to 0. So, and so we will write our F equal to, so we can, yeah, so we can write it as 1. Why am I writing this again? Okay. Yeah, I don't know what exactly I have done over here. Just give me a second. Yeah, so what, so essentially, okay, so let me just finish writing this 2I beta A minus 1 minus 2I beta B, okay. We also, if you remember, yeah, that yeah, the continuity, okay. So let's just go back to the continuity of psi, okay. The continuity of psi, what had it given us? It had given us that, okay, so the continuity for this, I don't know why I get so confused. Continuity for this, okay, had given us the condition that A plus B is equal to F plus G, right? Here also I need to put G equal to 0. So thereby I know that F must be equal to A plus B, correct? So let's now put this here, okay? So if we put this here, then we will get A plus B is equal to 1 plus 2I beta A minus 1 minus 2I beta B, right? So then we can just take the A's on one side, B's on the other side. And what will we get over here? We will get B plus 1 minus 2I beta B is equal to, over here we will get 1 plus 2I beta A minus A, correct? So this implies that we'll get over here 2 minus 2I beta B, am I right, is equal to 2I beta A. I hope I have written this correctly. And then, of course, we can just, we'll write B is equal to, I think the 2's will cancel out. So you will get I beta A divided by 1 minus I beta. Okay. So this is what you get for your this thing. So therefore, your B by A is going to be I beta upon 1 minus I beta, and therefore your reflection, okay, will be equal to mod of I beta divided by 1 minus I beta whole square. Okay, so this is your reflection coefficient. What will be your transmission? So transmission, of course, you can do it two ways. It'll be 1 minus reflection. You could do it that way, correct? Or the other ways would be to figure out what is F. Okay, F is nothing but A plus B, correct? And thereby it should be A plus I beta divided by 1 minus I beta A, correct? Which is going to be what? So it will be essentially 1 minus I beta plus I beta divided by 1 minus I beta A, correct? So which is going to be 1 upon 1 minus I beta A, which implies that your F by A is going to be 1 upon 1 minus I beta, or your transmission is going to be modulus 1 upon 1 minus I beta whole square. Okay, so either way you can do it, all right? I mean, whichever, kind of appeals to you, just go ahead and do it. So this is your transmission, this is your reflection. Okay, just putting in the form of the beta. Okay, so what do we get? Your reflection, of course. Okay, so let us just put in the form of the beta. So if you remember, we had done it in the earlier page. Your beta was nothing but, just 1 second, m alpha by h cross square k, correct? Yeah, and what was your k? Your k was nothing but root of 2me by h cross square, correct? So what we can do now is your reflection. Okay, I will not run through the whole simplification. I'm just going to put in the factor. You get actually 1 plus 2 h cross square e by m alpha square. Okay, so this is your reflection and your transmission. Okay, I actually hadn't written all these things last time in the notes, so good, you will have a repetition of this. So please look at today's notes for a detailed thing. Okay, this you get essentially 1 plus and then you'll have m alpha square divided by, I think, 2h cross square e. So please note that both the alpha and the energy of the incoming particle have a role to play here. Okay. So yeah. So this is basically what you have when, please note, delta function potential, we have written it as minus alpha delta x when your alpha was essentially negative. Okay. So this is the important thing to remember. Now, before we kind of wrap up the theoretical discussion of this whole thing, you can ask the question that what if that alpha was positive, right? I mean, you need not negatives, right? So you need not have a delta function well per se. You could have a delta function barrier, right? So let's just have a look at that. So this is now case 2. Okay, and remember it's the same Schrodinger
Over.
equation. Oh, yeah, as I told you, it's Yeah, I think there are some days where I'm not all there. Psi x, and then you had what? If you remember, it was a alpha delta x psi x is equal to E psi x, right? And what we did so far was consider the case of when alpha was essentially greater than 0, which means you had a Dirac delta well at x is equal to 0. Okay, so now what we are going to do is we are going to consider, I will not solve it in complete detail, but nonetheless it's less than 0, which means now you have a Dirac delta barrier at x is equal to 0. Okay, so this is basically what we are going to consider. Okay, so let me just make it clear. Okay, it is alpha less than 0. Okay, so what is the basic situation? So you have essentially, this is your x, this is your x 0, this is your v of x, correct? And you essentially have, should do it in a color pen, I think. Okay, this just heads off to 0. Okay, right, so this is heading off to infinity, right? Your v of x at x is equal to 0. So this is the Dirac delta barrier, okay, which you are talking about. Now let's just have a look at what the problem is going to be like. So you have h cross square by 2m d square by dx square psi of x, okay, is equal to so minus alpha delta x psi of x, correct, is equal to E psi of x. So what I'm going to do now, I'm just going to write this differently. I'm going to just cross square by 2m d square psi x dx square. Okay, so I'll take it on to the other side. So you will have essentially your alpha delta x minus, plus E, okay, psi of x, correct? So let's now just do this. D square psi by dx square is equal to minus 2m by h cross square. Yeah. So I'm just writing it as alpha delta x plus E psi of x. Now please note over here that your alpha is essentially negative, correct? If your alpha is negative, I will basically write now your alpha delta x as equal to some minus v of x. Okay, I'm just writing it just to kind of remind ourselves that that is actually negative, and not only is it negative, all right, it is very, very strongly negative, right? Yeah, so please look at this. Okay, alpha is less than 0. So I will write this now as equal to, okay, so let me just put an implies that d square psi by dx square, okay, is equal to, you have minus 2m by h cross square. We can write this as minus v of x plus e psi of x, correct? All right, so this now, let me bring in the negative sign. You will get essentially v of x minus e psi of x, correct? Yeah, so what if this is minus v of x, this is now positive, right? This is positive. And what do we know? That it is very strongly positive. So your v of x is of course greater than e always, correct? It is going to be greater than e. Whatever energy you can imagine, it is always larger. So essentially now this is a positive quantity, correct? Now can anybody tell me whether we'll get bound states? Are we going to get bound states? Remember, bound states would mean that you should be able to normalize. Scattering states are those like, free particle. You get basically free particle, modified free particle solutions. And you should remember that those are, they're oscillating even at, very large X, whatever. They are bounded, but they are oscillating. And so you cannot do anything other than a box normalization of those things. Okay. So hallmark of, just one second, I have to admit somebody. Hallmark of scattering states is that they are not normalizable unless you use box normalization. Okay, so you can normalize them, but you have to use box normalization. So which is why when you have scattering state, as I kind of was telling you, you go for reflection and transmission coefficients. Okay, that makes more sense to you. On the other hand, okay, bound states are normalizable. Okay, they are usually properly nicely bounded. They are not oscillating states. So in which case you can always get to normalize them. So now, any opinions on whether when I have a Dirac delta barrier at x is equal to 0, and this is basically my situation, right? This is the Schrodinger equation that I have written. All right. Can anybody tell me whether you will have bound states or not? Is there any mathematical way you can argue this out? I mean, the reason why I'm putting this up is also because there is a point of mathematical, there's a way of arguing this out. Any ideas? Yes, Chetan.
We get exponential states. So we get scattering states, not bound states.
Why do you say exponential states? I mean, you will get e to the power of ikx. I mean, you're saying oscillatory states, is it?
No, not oscillatory.
See,
exponential.
What do you mean by an exponential state? If you have e to the power of minus kx, where k is positive, okay, that is also a bound state, no? I mean, exponential states do not necessarily mean unbound states. Remember, your Gaussian is also an exponential, correct? Yeah. So exponential and unboundedness is not necessarily connected. E to the power of minus kx, if k is positive, is bounded. E to the power of plus kx, if k is negative, is also bounded. Okay. You have problems when you have e to the power of something like minus ikx. Okay. Or ikx, e to the power of ikx. Those are oscillatory, and they'll be oscillatory even when x is infinity. That's when you have trouble normalizing them. They're still bounded. They are valid wave functions, mind you. Okay, so here please note, the question is not a question of whether it's bounded or not bounded. Okay, I kind of didn't say it correctly. Question is not whether it's bounded or not bounded. If it is not bounded, believe me, it will not even be a wave function. Remember, that's a prerequisite of having a wave function, that it has to be bounded. So oscillatory functions are bounded. Even when you go to very large x, there is an upper limit and a lower limit within which they stay. Problem is you can't normalize them. So I was asking the question between having a bound state and normalizability. Any answers to that? Any thoughts? Okay, so the point is that, okay, let me see if I can explain it, because I just kind of came up with this before the class. The what you notice over here, okay, so the important thing to realize from this equation that I've written out, that d square psi dx square, okay, it is equal to some 2m h cross square, okay. I'm just repeating this thing, okay, minus e, okay, psi of x, right? Now this guy, the whole thing, okay, what we realize is positive, correct? It's always positive, right? Which now means that this fellow will have the sign of this guy, correct? So if psi of x is negative, d square psi by dx square is also negative. If psi of x is positive, d square psi by dx square is also positive. Okay, they have the same signs. Will you agree with me? Mathematically, just look at it. Will you agree that a double derivative of psi has the same sign as psi?
Yes, ma'am.
Yeah, okay. Now, what's the problem with that? Think about when you do your maxima or minima problems, right? Suppose you have a function f of x, okay? You know that when you have df of dx equal to 0, it could be either a maxima or it could be a minima, right? How do you know whether it's a maxima or a minima? What do you do?
Second derivative negative, then it's a maximum.
So that's right. So if you have a d square f by dx square, if it is less than 0, then it is a maxima. If your d square f by dx square is less than 0, then it is a minima.
Greater than.
Yeah, sorry, greater than. Yeah, it is a minima, right? Now, let us imagine that you are trying to, basically, let us imagine this is your x, okay? And you are plotting psi of x. Okay, so this is also 0. So if I plot above the x-axis, obviously I'm saying that psi of x is positive, right? So what will you imagine is a bounded situation, a normalizable situation, is when you can actually, what can you do? You can essentially, um, you have, even if it goes up, it has to come down. Okay, so that's when it's bounded, correct? Yeah. So let us imagine you have a psi of x going up and then going down. So if psi of x is positive, okay, then you require what? A maxima or a minima? You need a maxima, correct? Yeah. So which means that you will need this condition, that your the double derivative of psi of x with respect to x should actually be negative, which actually will not be possible here, right? Because it has the same sign. Similarly, if your psi of x is negative, for it to be bounded, okay, so if it is becoming more and more negative, you want it to start becoming positive at some point of time, right? And then you will have a normalizable situation, right? However, okay, what is going to happen is that you thereby require, so if psi of x is negative, as I'm saying over here, so let's imagine something like that, you need essentially, for it to be normalization, you need a position which is going to be a minima, and minima means that your d square psi by dx square should be positive, correct? But this is for psi is equal to, psi is negative, psi x is negative, correct? Now this guy contradicts that, okay? It doesn't make it possible, because it says that your d square psi by dx square will have exactly the same sign as psi of x, in which case when psi x is positive, d square psi by dx square is also positive, which means you can never have a position of a maxima. You will not meet that condition at all. So if it is going up, it will keep going up, or if it is going down, it will keep going down, okay? So you're not going to get into a condition of a minima when you're sorry, a maxima when psi is greater than 0, or a minima when psi is less than 0, which means that you will have trouble normalizing. If you're going to have trouble normalizing, it cannot be a bound state. Okay, bound states you should be able to normalize. All right, so this is another add-on which I don't think I have said specifically, but you people should remember this, that bound states, okay, are going to be normalizable, right? Here you are now getting into a situation where you have a wave function which can never be normalized, right? Unless you use box normalization. Maybe that's the only process. Box normalization promptly puts it in the category of scattering states. So what I'm trying to tell you is that the moment you invert the delta function, it was a well, you have now inverted to making it a barrier, immediately the bound state gets killed. So you will only get scattering states. Now look at the I think I have in the earlier page, okay, I have put down the reflection and the transmission coefficient, okay? The interesting thing, please note, is that the reflection coefficient and the transmission coefficient depend on alpha square. Now, to change the delta function potential, well, to a barrier, the only thing that you need to change is essentially the sign of the alpha. But the reflection and the transmission both depend upon alpha square. All right. So that means whether you have a well or whether you have a barrier with the same mod alpha, okay, alpha magnitude, the reflection and transmission coefficients actually don't change at all. So the scattering states practically remain unaffected. Okay. What will change is that in the case of the Dirac delta well, you have one bound state. In the case of the Dirac delta barrier, you have no bound states. Is this clear? Any doubts? I hope I didn't go too fast. I realize that I've already blown my time. Is this clear? Any doubts, please? So I'll just stop the share.
Can you repeat again what you said when you came to this page? Because
Okay.
my internet connection was unstable.
Yeah, I will just explain to you. So I hope you kind of agree that in the case of alpha becoming less than 0, which means that you have changed essentially the Dirac delta well to a Dirac delta barrier. Okay. What I tried to convince you is that you will no longer have a bound state. So now if you don't have a bound state, what about the scattering states? So what I tried to do was that I went back to these formulae, okay, of reflection and transmission coefficient. And this, if you remember, we did for the Dirac delta well, okay, when alpha was greater than 0, right? And we got these two formulae. What I'm trying to tell you is that look at alpha in these formulae. How does it appear? It appears as alpha square, which means that the sign of alpha becomes immaterial, right? Whether it's positive or negative, you're going to get exactly the same thing. So what I'm trying to tell you is that how did you go from a Dirac delta well to a Dirac delta barrier? You went by changing the sign of the alpha, all right? And as you can see over here, the alpha sign is immaterial here. So you get exactly the same transmission and reflection coefficients. So the funny thing is that change a Dirac delta well to a Dirac delta barrier. The only thing that changes is the bound state. The bound state, one single bound state which was there in the case of the well, vanishes in the case of the barrier. Excuse me. And the only thing that is there are the scattering states, and they are identical. So from the scatterer, okay, scattering states, you will not be able to figure out whether it is incident upon a barrier or a well. It's a little interesting, this whole thing. Okay. So whether it's a barrier or a well, exactly the same scattering states. The transmission and the reflection coefficients are going to remain identical. You will not be able to figure out whether it's a barrier or a well. But in the case of the well, the bound state, in the case of the well, there's one bound state. In the case of the barrier, you have essentially killed the bound state. It's not there anymore. Is that okay?
Yes. Thank you,
ma'am. Did you get it?
Yes, ma'am.
Okay. So I'll stop the share now. So please, yeah, I wanted to solve that problem. Okay. Doesn't matter. Have a look at the delta function problems that I've sent you. If you can solve it, try and solve it. But otherwise, those of you who haven't submitted assignments, my request to you is that try and submit it before the Saturday class, okay? So that when I discuss things in the Saturday class, so we'll take a break from this Dirac delta function, all right? And we will pick up the problems which I have given you for the Dirac delta, as well as the rest, one problem which I wanted to solve in class. We will pick it up on the next to next class, okay? So next class, kindly try and solve as many assignments as possible. If you haven't done it already, send it over to me, and yeah, we will discuss those problems. So that's the idea. Is that okay? Yeah, so I'll stop the recording.